Okay, hi everybody. I would like to talk to you about the vertical sun at small scales. This is some work that has been done here at the National Observatory of Athens in collaboration with Georgia, Yanis Kondogiannis and Ioannis Dekanalis, our PhD student here, and also Elena Komenko from the Institute de Astrofísica de Canarias. We know that, small-scale vorticity on the sun occurs because of convective motions. The visual aspect of convective motion on the solar surface is, of course, granulation. And as we know, in granules, we have hot plasma rising at the middle of the granule, and when it reaches the surface, then it cools down, and then it starts flowing back to the solar interior through the intergranular lanes. This downflow, during this downflow, because of conservation of angular momentum, this downflow occurs according to the so-called bathtub effect. It's like a bathtub being evacuated, from its water, and that creates basically an intergranular vortex flow. So a vortex flow that is located at the intergranular lanes. There are simulations that actually this evacuation at the intergranular lane produces an intensity enhancement, and I'm showing you up here such a simulation that was produced with the Cobalt code from Calvo and al. In 2016. You can clearly see here an intensity enhancement, which has nothing to do with magnetic fields. It's a non-magnetic bright point. Now, usually, right at the granular lane, we have also the emergence of quiet sun magnetic fields. And when an intergranular vortex flow occurs, then if we have a collocated magnetic field line, as Wedemeyer and Steiner showed in 2014, then you start putting into rotation the magnetic field lines above, and you create a magnetic tornado. And these magnetic tornadoes basically extend, as Wedemeyer Bohm showed in 2012 in his Nature paper, up to all atmospheric layers, up to the low corona, and there are visual and observational signatures of that up to the low corona. And I'm showing you also two other works that have been produced here at the National Observatory. One from Park et al. In 2016 that shows such observational signatures of magnetic tornadoes up to the magnesium line, which is a transition line, and also a more recent work by Tziotziou et al. That shows the response of such magnetic tornadoes up to the low corona. Now, when we look at the photosphere, the photospheric signatures are seen in lines like the wings of the calcium lines, or the iron line, or the G-band line. And usually it's observed by the spiraling motion of the magnetic bright points, as we see here and here. So we see actually, these magnetic field lines following a rotation, and usually giving spiral patterns like the ones that Bonnet et al. Reported in 2008. Those were actually the first observations of tornadoes on the sun. Usually at the photosphere, there are around 90 such vortices per square megameter, with a lifetime of almost 5 minutes. Up in the chromosphere, usually magnetic tornadoes show like rings or spirals or fragments of spirals. And you can see here observations by Wedemeyer, Bohm, and Rupert van der Voort in 2009, where you can clearly see these very nice magnetic tornadoes, spiraling magnetic tornadoes in the calcium 28542 line. Usually these chromospheric swirls, as they are known, they have dimensions of a few thousand kilometers, average lifetimes of about 10 to 12 minutes. And as the Wedemeyer report in 2012, usually you have something like 11,000 events on the solar surface at all times. Only lately, 3 years ago, the solar physics group here at NOAA observed these magnetic tornadoes for the first time in the H-alpha line center. So what you see here is such a vortex flow that has a quite large radius of 3 arc seconds. It has a very long duration, which is at least 1.7 hours. That's actually the whole range of our observations. And it shows also a significant substructure, which is shown here with these colored circles, which is small chromospheric swirls that have exactly the same characteristics as the one reported before. Later on, H-alpha magnetic tornadoes were also verified by a paper by Sethi et al. Some six months later, basically. So now people started observing chromospheric swirls also in this very complex and very abundant line like the hydrogen line on the solar surface. Now, the proper estimation of the chromospheric swirl population, I told you that Wedemeyer estimated something like 11,000 such structures, basically suffers from two things. One is observational limitations. As you can see in this cartoon by Wedemeyer, basically the solar chromosphere is full of flows like spicules, the canopy, and other structures, jets, and so on. So basically, it's very hard, to observe vortex flows among all these structures. The second thing is that there are detection difficulties in chromospheric lines, meaning that although in the photosphere it's very easy to derive the velocity field and then calculate a metric that basically defines vorticity, like vorticity itself, but because vorticity also incorporates shear motions, there have been other parameters suggested, like the maximum vorticity method, the gamma functions, the delta Q and lambda 2 criterion, and so on. But the important element in all these detection methods is that they depend on the velocity fields. So you have actually to use some local correlation tracking technique to derive a velocity field, and from that velocity field, calculate the loci of vortex motions on the sun. So as I have already indicated, past studies have indicated something like 3.8 chromospheric swirls per 1 arc minute times our 1 arc minute field of view. This is the paper by the Nature paper by Wedemeyer, where visual inspection was used to find these population numbers. We have acquired some new observations with the SST telescope last year, and these observations that were taken simultaneously in the H-alpha line and the calcium 8542 line indicate that there are more than 80 swirls within the same field of view. You can actually see in this very beautiful image that the whole basically field of view shows these little vortex motions. This has been, we have been able to find these large numbers because of a new automated detection method that is based in morphological features. Therefore, it requires no velocity field estimation. And Yannis Dakanalis is going to later on to discuss this method in more detail. Now, we know from simulations and observations, and I have already mentioned that the number of vortex motions of the photosphere is much larger than the numbers of the chromosphere. As I told you, Bonnet showed something like 90 vortices at the photosphere, whereas Wedemeyer showed that there are something like 4. So we have to keep in mind that the formation of intergranular vortex flows at the solar surface is a prerequisite for the formation of magnetic tornadoes, but not all of these intergranular vortex flows actually result to magnetic tornadoes. First of all, the formation of a magnetic tornado depends on the local magnetic field environment. Open field topologies are favored, and you find such field topologies, for example, in coronal holes, because these open field topologies do not actually they facilitate the unimpeded rotation of such structures. I told you about these new observations. So is this the case? Although you can see here on this yellow rectangle the field of view of our observations, and although visually at the beginning it looked like a coronal hole, when we looked at the solar wind velocity in the preceding days, we see that actually it doesn't relate to a coronal hole. Furthermore, some magnetic field extrapolations in the region showed that this region is basically dominated by open magnetic field lines as required, except of two loci here that have rosette formations with spicules. And actually in these two rosette formations, we don't see any vortices at all. We tried to explore what is the role of the magnetic field by incorporating some 3D magnetoconvection simulations that were carried out with the Mansa code. This is a code developed by Elena Comengo at ESA, and we used three different setups. One with zero Gauss seed magnetic.
Costa, 5 minutes.
I have put the clock and it says 11. Okay.
11 till the end.
Okay.
You have 5 minutes.
Okay, so we have three different setups. A zero Gauss seed magnetic field, therefore, surface dynamo simulations, a 10 Gauss and the 50 Gauss seed magnetic field. And we looked at vorticity by taking the Q criterion, which takes into account the symmetric and anti-symmetric versions of the velocity gradient tensor, where omega defines the vorticity tensor and des defines the vorticity strain, the strain tensor. I'm showing you here the results of these three different simulations. So on the left, you see the surface dynamo, on the middle, the 10 Gauss and the 50 Gauss on the right. And with yellow and orange lines, I show you the Q over beta parameter. And as you can see, the surface dynamo, what happens is that you have the creation of lots of horizontal vortices near the solar surface, while when you increase the magnetic field, then you get very coherent structures starting from the photosphere and extending up to the chromosphere. The top boundary here is at 1.4 megameters, so basically at the chromosphere. Now, since we have a magnetic tornado, we have braided and twisted. We have a braided and twisted magnetic structure, and such structures can drive and foster a wide variety of oscillations and wave modes, and amongst them quite a lot of different Alfvénic type modes, so king waves, sausage modes, and torsional Alfvén waves. We have 2 years ago we have made an oscillatory analysis in the vortex flow that I showed you before. And by looking at the mean oscillatory power per period within this vortex area, we see that there is clearly power enhancement seen up to 10 minutes, so at periods of 500, 600 seconds, well above the acoustic cutoff period of 180 seconds for the chromosphere, suggesting that there are actually other wave modes different than the acoustic ones, so magnetoacoustic wave modes. Furthermore, we have employed a cross-wavelet phase difference analysis, and we see that within the vortex area, the cutoff frequency, which is indicated by this yellow line, is basically between 2.5 and 3 millihertz within the vortex area. And when we combine this with some observed swaying motions that we see at the structures within this vortex area, the natural interpretation of these swaying motions and this lowered phase difference is basically the suggestion of king waves. Third, the phase difference analysis, when we do it in H-alpha and in the calcium lines, and for different vortex areas, so within the whole vortex area and also the substructure seen as this red, green, and Kian circles, in all cases, we see that the phase difference is positive. And by taking this formula, we basically calculate speeds of the order of 20 to 30 kilometers per second that are compatible with Alfvénic type wave speeds. What this analysis also indicated is that there is a coexistence of localized torsional waves, and this has already been suggested by simulations in the paper by Fedun et al. In 2011, as we see on the left panel. But also it has been suggested that when you look at phase differences of full width at half maximum oscillations of the H-alpha profile, then you should expect at the opposite boundaries of the vortex flow to have 180 phase difference delay. And actually, within one of these substructures, the ski and swirl, we see that actually we do achieve this phase delay, suggesting that there are also torsional Alfvén waves within the structure. So the observational result seems to be consistent with numerical simulations that suggest that different MHD wave modes can be excited simultaneously within such structures and also coexist in the same vortex tube. Now, this has, of course, implications for the transfer of energy higher up. It has already been suggested a decade ago that magnetic tornadoes transport energy from the sun surface up to the corona, contributing to the heating of the different layers of the sun. Wedemeyer, Bohm in his Nature paper, and more recently Nitin Yadav in 2020, using different sets of simulations, they calculated a net positive Poynting flux of 440 watts per square meter, and Nitin's calculations were a little bit higher, giving a net Poynting flux of something like 7.5 kilowatts at the height of the chromosphere. We have explored DAR simulations, and DAR simulations indicate that the total Poynting flux is more than 10 kilowatt per square meter at the chromosphere, while the net Poynting flux is almost 1 kilowatt per square meter at the chromosphere. So these numbers are well in accordance, with numbers that previously reported in literature. But we have to keep in mind that the numbers of vortices that we now find are much higher than previously reported. So coming to my summary, vorticity on the solar surface that results from solar convection seems to be an omnipresent process. Magnetic vortex flows seem to be favored in open magnetic field topologies. Therefore, this implies that vorticity may be extremely important when we go to solar latitudes and polar regions, where unfortunately projection effects do not allow us to observe them directly. As have already indicated, there seem to be a higher number of magnetic vortices in the solar chromosphere, chromosphere and atmosphere than previously thought. Such structures foster a wide variety of Alfvénic type modes, and there seems to be a considerable transfer of energy higher up. And given the higher population estimates, this means that these structures may play an important role to the heating of the sun's outer atmosphere. And one final point that I want to make is that their significance in solar wind driving at polar regions has to be further investigated, because there are studies that actually do link solar wind acceleration with Alfvén waves that are very easily created in such vortex structures. Thank you.